Hi everyone, welcome to my presentation about animation engineering. I'm Robert, I'm a software engineer at Pixeland Games. I used to work as a Scala engineer in one of software houses in Poland. However, things happened and I switched industries and now I make games using Unreal Engine and C++. Quick reminder, if you have any questions throughout the presentation, use the code below with the code GeeCON. Today's presentation is going to be all about animation. We're going to talk what an animation is, how 3D animations are made in games. We'll talk about animation blending. We'll see some animation graphs, talk about driving character movement through root motion, and talking about more advanced features like motion warping, delta correction, and we're getting into the procedural territory of inverse kinematics. And lastly, I will show some examples of how games approach animation optimizations. So let's get started. What is an animation? You might remember that an animation is essentially like a sequence of images displayed over a shared duration. However, this creates like an illusion of motion. However, this isn't the type of animation we're going to be talking about today. Because for us in 3D games, 3D animation is all about skeletal animation. So let's try to understand how these are created. Before we start animating, we must first have something to animate. So it just happens so that we have an artist friend that will create a mesh for us. A mesh is a 3D representation of an object that's essentially made of vertices, edges, and faces. People normally refer to it as a model. But how do we make it move? Generally, a mesh inside is empty, like I am. However, we can feel it. And we can feel it with a skeleton. And the skeleton is a hierarchy of joints and bones. Joints are the rigid objects that animators will translate, rotate, and scale in order to create the keyframes or the key poses for an animation. Every joint has exactly like one parent apart from the first joint in the hierarchy, and manipulating like every joint will manipulate the children. There's also the concept of bones, and bones are the empty spaces between joints. In Gamedev, unfortunately, the terms are used sort of like synonyms, so quite often people say bones and joints and quite mean the same thing. And there's a little bit of trivia. How many bones are there? This thing doesn't, sorry. As a little bit of trivia, how many bones are there in a humanoid skeleton like you have seen? It's a humanoid skeleton of a mannequin from Unreal Engine. It's something that's there by default. And it turns out that's over 100 of bones in there, so you can sort of see the scale of how many bones there are actually there. So now we have a mesh, and we have a skeleton, but we have no ways to associate them. And we can fix this through the process of skinning. It's a process of binding mesh vertices to skeleton data. It's usually done by a skinner. It looks a lot like what you see on the screen. The skinner will align the skeleton and the mesh in a similar pose, the bind pose. And if you play games, you've probably heard of a T-pose. And T-pose is an example of a bind pose. The whole process sort of resembles it sort of resembles painting in the way that the skinner will paint over the model, and that will control, that the amount of paint will control how much a particular joint will deform the vertices of the mesh when they move. And even though it is made by a skinner, usually like in smaller studios, etc., there isn't a person that specializes in that, so it will be on the hands of the animator to actually do it. And because it's the default pose in which we do the process, you might also encounter, that's why you often encounter these poses in video games where something goes wrong with an animation system. There's one more thing that we can do before we start animating, and that is to create a rig. Rig is essentially a set of controls of higher abstraction over the skeleton that aims to create the natural movement and the connections and constraints between different limbs and bones in a body. The creation of a rig sort of resembles like domain modeling in the sense that we are trying to model the domain of how a character is supposed to be moving. And this is made so that animators won't have to manipulate every single joint, and instead will have like a bit easier to use controls to create the key poses. And this is usually done by a rigger, but quite often that's an animator as well. And eventually, now that we have done our rigging, we can start putting together an animation like this one. However, everything so far that I have shown has been done by an artist of sorts, and I promised some engineering. So let's try to think what we need to create, to play an animation in code, and how we could sort of imagine like a very bare bones and like a very simplistic animation system. And to do that, we need a couple of things. We need to define a data structure to represent the animations. We need some way to load the animation data from an animation, and usually in a format such as an FBX. We would need some way to display the animated skeleton, and we would also need a controller for animation, something that can play it, that can stop it, that can loop it, etc. And our keyframes, they are essentially like translation, rotation, and scale data for every joint, for every pose in the whole skeleton. And then our animation clip is essentially an array of animation poses played over a duration. We might also need some kind of reference to a skeleton in there that has its own information about the joints in the hierarchy. And once we have all of this, we can imagine an animation controller, a very bare bones animation controller that's cycling through different animations, different animation poses, and is updating the skeleton data. However, as I mentioned, it's a very simplistic idea. And I'm showing this just to paint a picture. This is like something that would be, there's something that's the animation system, if you strip away like 99% of features from the current like mainstream full-grown animation systems. But it's still nice to know that this is all what's going on there, cycling through poses. And as we talk over all the different features in this talk, I would like you to try to think how this would change the original code that I have just shown. And this brings us to animation blending. The problem is that games might not run at a stable FPS rate, and they quite often do not do so. So if you're choosing this, if you're looking at the code that we have, it's going to cycle through all the animations, sometimes faster, sometimes slower. And we would not like this. We also wouldn't like our animators to have to create a keyframe for every frame of the target FPS rate. So they wouldn't want to be exactly like 60 FPS for 60 frames for a 60 FPS animation. And the answer to this is interpolation or blending. The way it works is that since our keyframes are in SRT format, so they have this scale, rotation, and translation component for every joint, we can linearly interpolate between the scale and translation components. And for rotation, which is often represented as quaternions, we're going to use a slurp, which is a spherical linear interpolation. However, that's because the sort of the geometric interpretation, in a way, of a quaternion has something to do with a sphere. At least that's what you can find online on it. And all these blend types are not necessarily restricted to being linear blends. In a full-grown system, you would have multiple ways to choose the blending function. There could be a cubic or sinusoidal blends, and they are better for different things. So for completion's sake, you can see the equations for LAP and SLAP. However, this isn't a talk about mathematics, so I just want you to be aware how more or less this looks like and what's the similarity between the two. And the result of such blending you can see here. The middle pose is a blend between the first and the last pose, and you can sort of see it by the position of the front leg and its rotation. It's somewhat in the middle between the two. And now that we can blend multiple poses together from the same animation, how about blending multiple poses from different animations? And the most common thing that you can encounter in games, if only the animation would play, but it doesn't want to for some reason. Sorry for this. Not quite sure why. Is it going to play it? No, it's not going to play it. This is the type of thing that tends to happen when you test the presentation beforehand. Show all controls, and let's try to play it manually then. So yeah, this is the type of blend space that's in games. It's a walk-run blend space. It's essentially blend space is essentially a parameterized space which has an input parameter that acts as the blending factor. And in this case, this factor is speed. So by inputting different speed values, the more running the value our output animation is like. And we blend between multiple animations here just to have this smooth transition between different states of running. But now the problem is, will these things blend? Will different animations blend together well? And it turns out that it isn't necessarily the case. And I will unfortunately have to play every single animation by hand, it seems, every single video here. I'm not sure why. And if you choose the wrong animations, there is going to be a bad result. So if you have these two animations in here, so the middle result will look something like this. And it's unusable in games, essentially. It's something you wouldn't like to see. And this is because, in most cases, for different bone paths in an animation, there should be some continuity in order to have a smooth transition between animations and for it to look actually good. You can probably imagine by now that since games have all these different animations in them and all kinds of states in them, it's kind of hard to manage all this complexity. And in the first generation systems, first systems with 3D animations, all of this complexity was managed through code. So you can imagine a code that essentially has calls to play animation somewhere and has this sort of distributed animation graph of animation states in there. However, at some point, there was an evolution of this. And animation graphs or blend tree systems were created, which are a visual help for programmers and for animators to actually see what's going on. Here you can see a locomotion animation graph from Lyra, Unreal Engine 5 learning project from Epic Games. And since it's just locomotion is everything related to walking, flying, jumping, falling, start, stopping, etc. So all kinds of movement-related things. And there's already this many states and already this many conditions and edges between different states. And I'm not even mentioning combat, interactions, traversals, etc. As you can probably imagine, there's quite a lot of animation graphs like that throughout the whole project. And here the animations are actually playing. Well, at least that's something. So here is the animation graph in action from the same project. You can see how they provide the runtime information in what kind of state we are in and how long we've been there, which is really helpful for daily work with animations. But there is one problem with animation. One elephant in the room, you could say. And that is that characters in the world 3D characters in the world are not defined by the position of this mesh or of the skeleton. Instead, every character in pretty much every video game is essentially a capsule that's used for all sorts of collision detection, etc. And the mesh is like a little bit of paint on top, so just so we can have some visual feedback. So we wouldn't want a case like this, because currently if we play an animation, the mesh is going to like walk into walls, do all kinds of crazy things like this, and we want to avoid this. We would want to have something like that, where we are actually moving with the capsule. And to figure out the answer of how to do it is to understand root motion. And to understand root motion, we need to answer a question how to figure out which way a skeleton is moving. And there's multiple ways we can approach this. Like, for example, you could think about this as in every animation, there's a lot of bones moving simultaneously. Maybe we can take all their movement and figure out a direction by summing it up, for example. But that wouldn't necessarily produce any sensible result. And there is a simpler solution to this question. And that is, maybe we can just pick a single bone in particular and analyze its movement. And based on that, we can figure out which way that skeleton is moving. And that is what root motion is. We are adding an extra bone to our hierarchy, a root bone, which is going to be used for movement detection. We're going to extract its translation, its rotation, into like a separate place. We're going to then remove it from the animation. That means that when we play an animation, it's going to play exactly at the position of the capsule. However, we'll still have all this data separately so that we can sample it and use it as movement input. So then we can have our character actually moving. This, however, means that animations need to be prepared, taking root motion into the account, and that means more awareness from animators and like more teamwork between the gameplay and animation engineers and animators to make sure that we have exactly the root motion that we need. Otherwise, things might start looking wonky or break or just not work at all. So here's an example of a root motion animation. You can see the root moving by following the red path on the animation in here. You can see how it's moving horizontally. And here's another example of a root motion animation. And before I even joined Gamedev, something that I always wondered was how games achieve like movement for very weird paths, like a curved one here, because the root is actually moving in like this pendulum way, in a sense. And I was thinking that maybe we control this all through code, and someone is writing like some very intrinsic, very interesting ways to like move on this curved path. However, this isn't the case. We're just creating an animation and using it to drive character movement. And this is now turning into this kind of discussion. How should we move our character? Should we move it through code? Should we move it through animation? And there are different trade-offs that we can make. If our character is moving through code, it's going to be extremely responsive. We're going to be able to do things such as turn 180 degrees instantly. However, we will have lower animation quality because there is no blend that is going to look well if it's that extreme. We might also introduce foot sliding. Foot sliding is a situation in which an animation, the speed of the animation does not match the speed of the character in the game. And that results in a situation where visually the feet move sort of in a sliding way on the ground, and that is seen as bad quality. And there is really a lot of work put into the games currently just so you don't see the feet sliding on the ground. But on the upside, it does not require any animations to work. So we can build all of our systems and we can remove all the animations from them and they will still work. However, if we are going to move our character through animation, this is going to be less responsive. We will need to wait for the animations to finish quite often. There will be no foot sliding because, well, the animation controls everything, so the movement is matched to the animation speed. Therefore, we'll have higher quality of animations. But it would all stop working if we accidentally or on purpose remove the animations, because we would no longer have the root bone data. So we would have no way to drive the character movement. And it turns out that in most games, actually a mixed approach is taken. So we will have parts of movement, for example, locomotion, done through code. And we'll have parts, like especially like skills in combat or specific interactions or combat or traversals that are going to be done with root motion. But there is, once again, one problem with root motion, and that is that animations are created with a certain distance in mind. For example, if you have seen this sort of cartwheel animation or some jump animation, it's made with like 5 meters in mind. It's a jump for 5 meters. Now we would like to repurpose this animation for 3 meters, for 2 meters, for 1 meters. And we can't really do that because we are going to move exactly that distance through root motion. We could then maybe try to go back to code-driven movement, and it will look worse, but will be more flexible. And with root motion animations, we would need our animators to create lots of animations to cover all these cases. And still, then would be situations where we maybe want to jump 1.5 meters and not 1 or 2 meters. So it's very restricting. And to fix this, there's the concept of motion warping and delta correction. So there are 2 terms for the same thing, essentially, but there are a lot of things in animation engineering that are not really standardized in naming. And the whole concept of delta correction is that we can stretch or shrink that root motion data to fit different goals. If we do that, we can reuse the same animation in different scenarios, and it turns out that it's actually the backbone of many traversal features in games nowadays. The way it looks like is that imagine we have like a sort of skip jump animation like this one with the root motion that you see. And we can have it, well, if it worked, but since that some still are stopping for some reason, we can have it work for medium distance like this one. I will let it play through a few times. We can have it work for a short distance like this one. And we can have it work for absurdly long distances. And we are still going to be playing this animation is going to start and finish in appropriate times. So how does it work? Essentially, we take the difference between the final position from root motion data and the specified goal in the world. We can take this difference, or delta, that's why it's delta correction, and divide it across all the animation frames in an animation. This will mean that every frame of an animation will move us closer to our goal. And in full-grown systems, there are usually tools that allow us to specify which parts of animation should we apply this motion warping and delta correction to. So we can have, for example, horizontal delta applied to this part on the animation, and then there's nothing else later. And then we can have another part that's vertical if we want to have some kind of like a jump on a very tall object. This is something that we might want to have. And some systems, and in some cases, this will introduce foot sliding. And we can avoid this if we apply root motion to situations in animations where the character is context-free, which means essentially that they are not interacting with anything, they are not supposed to be touching anything, and that they are essentially in air. So here you can see an example of a motion warping window applied to this particular animation. You can see it by this pretty much 2 red points on the screen, and you can see that this is like more or less in the in-air part of the animation that's going to be stretched or shrinked. And all this delta correction essentially is manipulation, like procedural manipulation of animations. And when we talk about procedural animations, there's the important point of the important thing that there's here is inverse kinematics. And let's start by defining kinematics to know what inverse kinematics is. And it turns out that they are actually the study of motion, but ignoring all kind of physical forces that are causing this motion. So it's essentially an analysis of position, velocity, and acceleration. And kinematics deal with chains of rigid bodies. And in our case, in animations, because it originates from robotics, but for computer animation, that kind of chains that we have are the skeleton body parts. So like a chain from the shoulder till the hand is going to be one example of a chain. There's multiple bones there that form a chain. And the motion of such rigid object, rigid body system, can be found using forward kinematics or inverse kinematics. Forward kinematics is a situation in which we are trying to solve for the end effector's position. End effector is the ending element of the rigid body chain. We have the start position, we have the bone lengths, we have the angles between them. And you can probably imagine that there is trigonometry in there that we can use to calculate the end effector position. However, for inverse kinematics, we already know that position. And what we do not know is the angles. And we're trying to figure out what the angles are and how to position all the multiple bones so that it will align. There is an algorithm for this, multiple algorithms, but the simplest one that I could find is called Fabric, which is forward and backward reaching inverse kinematics. It essentially is a heuristic approach to finding like an approximation of a solution here. The way it works, it has like two phases, backward and forward one. We're going to be going from the goal till the previous point in a chain. So here on the video, you can go from goal to P2, and then we'll have another new point, potential new point. We're going to repeat this for the rest of the points in the chain. And then we're going to do the same thing from start, but now using the currently calculated points. So you go from start to P1 prime, etc. And over many iterations, we'll get closer to our goal. But you may be wondering, why? And the answer is animation quality. You can have more grounded characters in the world if you look at their feet currently that respond to different terrain. And there's a lot of work like this done so that the characters' limbs will respond to different terrains so that there's more immersion in the game. You can see the feet responding to difficult terrain, and the dev character isn't floating, or what would usually happen in like older games. And the last thing that I want to talk about is animation optimization. There are different techniques, and it's like a very broad topic, but I've got a few examples. And thus, in every type of optimization, it's good if we know our environment and what we optimize for. So, for example, if we are, for example, working with Nintendo Switch, and that guy doesn't have really a lot of memory or disk space, some systems might then use scale compression. It's a technique that essentially throws away all the scale component from different transforms in an animation data, because games very rarely scale their animations. So we can save on 2 or 3 floats of memory from every bone, from every animation pose, for every animation, and there can be thousands of animations in the game, so there's quite a lot of space actually saved. We can also do animation cooling, which essentially means we do not play animations for characters that we do not see on the screen, or that our player cannot see on the screen. This can help save us on the CPU time. We can also do animation streaming. We do not have to load every animation in memory. Once again, there can be thousands of them, so let's just load the ones we need. There are lots of algorithms that deal with like significance or relevance. That's something that designers and developers have to define. A very popular example in games that want to save on the CPU or some other resources is that when there are characters that are further away from a player, they're going to be playing their animations at lower FPS rates. And this will help us save save on the resources, and you will see a short video of this in a moment. In Unreal, for example, there are systems that allow you to play exactly the same animation for multiple characters, so at the same time. So if you can imagine like an army moving, for example, an army of stormtroopers, they're going to have synchronized animations, and that means we will not have to control every single animation at the same time. And the last thing that I have quite recently read about is GPU instancing. And it's a technique where we can essentially reduce the number of calls to the GPU to draft multiple meshes. That allows us to have like an absurd number of meshes on the screen at a single time. There's an issue, however, because it does not support animation. And what people figure out is that we can bake that animation data into mesh data. So we are sending like mesh data together with animation data to the GPU, and it allows us to play animation on multiple characters and save on the draw calls. And we'll also see a video of this in a moment. So here you can see the example of the significance issue. It's the latest Pokemon games. Especially at the start of the video, if you look at the two bigger Pokemon in the distance, you can see them playing animation at lower rates. And as we get closer, the animation is turning a bit more smooth, and it's actually like better at the end. So we'll let it play through one more time, and we'll move forward. And you might have heard of Ultimate Battle Simulator too. And this is a game that, from what I read, uses the GPU instancing. And this is like a result that you can have an absurd number of meshes, an absurd amount of animations going on at the same time, and it's all at a decent FPS rates. And quite recently, there was also an article or a Reddit post by tirelessly about animations of particle systems. This is essentially like the example of GPU instancing, where he managed to get like a huge flock of deer running around together. And in my opinion, at least this looks amazing. So there's this whole animation engineering iceberg, because all the things that I have told you about so far could have been its own presentations, and there's more. There are physical animations, which are a whole different can of worms. Essentially, you have physical simulations on the skeleton, and you blend between different animations and the simulated parts, and it's causing all sorts of issues. There are modular characters. We can build characters from different parts, and they need to animate well. There is something called motion matching, which is called the future of animation for video games. And this is what most biggest AAA studios are working on currently. Essentially, it's a system of machine learning that will analyze and match your character's movement in the game to an animation from a database. Usually, like humanoid characters are getting mock-ups, so there's like motion capture session where they put an actor in a suit and they will like record all sorts of animation then, and then we'll have an algorithm matching this animation with motion data in the game. And there's a whole topic of animation compression, more than just the scale compression that I have mentioned. There are a lot of gameplay features built using animations, and like works completely different for like a fighting game, and completely different for a game like Dark Souls. There's yet another completely different topic, different kind of forms in the form of facial animation, which are not done by skeletal animation, though they can be. But the problem in here is that there would be too many bones in a face to make it like sustainable, manageable. I think that would be a better word. So there are different techniques to use in case of facial animations. There's a matter of retargeting animations, which means reusing the same animation for different skeletons or for similar looking skeletons. So there can be issues that occur there. If you would like to learn more I can strongly recommend the book Game Engine Architecture by Jason Gregory. It has a great chapter of animations. And after this presentation, you might want to watch Animation Programming Basics by Bobby Angulov. It's essentially a 3-hour-long talk on similar things that I have talked about today, but a bit more in depth, and it's a little bit daunting at times. If you have nothing to do with animations, at least. There are also talks on GDC, Game Developers Conference. I can recommend Bringing Hell to Life Doom, which essentially tells about delta correction usage in latest Doom games and what they used it for and how they came up with the actual thing. I can also recommend player traversal mechanics in the vast world of Horizon Zero Dawn. They talk about all sorts of gameplay issues with implementing animations, how they, for example, correct the trajectories of different player actions like jumping so that they can not fail, essentially. So if you can imagine like jumping on a very weird or like small terrain, there's a high chance of you falling. They procedurally correct that. They talk about how they modify the pathfinding for all the mechanical beasts in the game, so that they have a more realistic turning animations for different like beasts, mechanical beasts in there. And that's about it. I was quite fast this time. Do you have any questions? And I will try to find the Slido. You mentioned you were a Scala dev. What was the most difficult for you when you started your journey in game dev? So it's an interesting question. I would say there were many things that actually weren't difficult, and strangely, a lot of things made sense. They were rather simple, and I liked it a lot. But as you dig deeper into all the game dev knowledge, there start to be certain problems. And for example, there's like limited access to information. There isn't that much knowledge sharing in game dev. There are the conference presentations, etc., that I have mentioned, but there are not, like, for example, a lot of books in there. And if you want to get like expert level knowledge, then maybe there are like a few people in there, or a few people in Poland that, for example, have the experience of creating a complete animation system from scratch. And it's not that many, and they do not necessarily make presentations on conferences. So if you want to go through this, you need to start doing a lot in your own time, and you need to start going through white papers to try to understand that this, for example, kinematics from robotics have some usage in animation, etc. How much math there is in game dev? So the daily work, it depends. I would say it doesn't have to be that much. If you are a gameplay engineer, you're going to do a lot with like vectors and vector-based math. You're hardly ever touching matrices, etc. However, if you are, for example, a rendering engineer, so you do a graphical part of game engines, there may be a lot, and there's a lot of advanced math in there, especially if you work on some new features. For animation engineers, if you are creating stuff like delta correction, you might want to think about like advanced math to how to spread the delta over different frames, and there can be a lot of it. But for the most part, it's not that much math. Or the math that you actually do is quite simple, and you can just have a 30-minute watch on YouTube, and that's enough for daily work. What exactly is a traversal? So traversals refers to objects or like interactions in games, skills that deal with character traversing and displaying like a state. So if a character is like vaulting over something, that vault is a traversal. If a character is like going on the ground through a tunnel, that might be a traversal. If a character is wall climbing, that's a traversal. yeah, that's kind of situation. Certain jumps, if they are scripted, they may also be considered traversals. How do you handle changing FPS rates? In what way? In what scenarios, if you could add to this, it would help. Because I mentioned that in case of the skeletons and the animation, because we are blending between the two, that sort of handles the displaying part of the animation. How do you attach something to the skeleton, like a weapon to a character's hand? So it turns out that when I was talking about skinning and skeletons, there was a lot of like binding of the mesh data to the skeleton data. But what if we had bones in there that weren't connected to any part of a mesh, and they were sort of virtual bones? And it turns out that they will still be here. They would still be there. They will still be in the skeleton in the game, and we can get the position of such bones. So if we have that kind of bone that's attached to a hand bone, for example, the hand bone is the parent of like a virtual bone in here. We can get the position of the virtual bone. We can then move the mesh, for example, of a sword to that position and apply like proper rotation, etc. And we have now a character that's running with a sword. That usually means the animators will have to take into account that in this particular animation, the character is meant to be holding something, so they will compensate. It will not be too random. Are there different specializations for animation engineers, like Skinner rigger for an animator, or do you take care of everything? Yes, and there are essentially two jobs in Gamedev. One is animation systems engineer, which implements all the features like delta correction, like all the underneath engine stuff. And then there is just animation engineer who deals with gameplay features. So it will take all the like, for example, animation graphs. It will take the delta correction that was done by animation systems engineer and will use it to create gameplay systems and things like skills in combat, etc. Or will deal with character movement in a sense that they will program all the character movement. Maybe they will do physical animations in there and physical movement. That kind of thing. What surprised you the most when switching to Gamedev? Do they use Kubernetes? I remember one job offer from Gamedev that used Kubernetes, but it's like depends on the game. If the game is more online, they might be using this. What surprised me the most, I guess, would be that even though there were less like abstractions and less, you could say, domain modeling, and the code was simpler because it was C++ and didn't have many advanced features, like for example Scala would have, it was actually simple to understand. You would just go in there, 500 lines of a function that does something with an interaction system, and you read it for some time, and you actually understand what's going on in there, which wasn't necessarily the case with Scala and implicits and some other abstractions. How do you debug those fancy animation graphs? Is there any special tooling? There is a couple of things, and like, it will depend on the engine if it has something implemented. One of these things is that, as you have seen in animation graphs, there's live preview. And so you can see what kind of animation is happening there. However, for the most part, it's going to be looking for something. You will know that the animation breaks at a particular moment. So there's a lot of knowledge required from using those tools. And there's one feature in Unreal that's sort of experimental yet, and that's Animation Insights, which is like a profiler for animations, and it's trying to show you data of how much this animation clip in this particular state was playing for. So you can sort of start to understand which animations were playing, which might be blending together, etc. But it's still experimental. Can you unit test animations? That would be hard to do. especially because there are different blends. Like in some cases, you will have situations where you take like 90% of one animation and 10% of the other, but then the FPS will drop and it will, for example, totally turn upside down. And the resulting poles will be composed differently. So it will be hard to unit test it. And as far as I know, no one is unit testing animations. But it's a general problem of tests in game dev that there are not that many being done at all. But if there are any, that usually focuses on the gameplay. We still need QA to make sure that all the animations like feel good, that the game feels good. And essentially, a game is like an extremely big state machine, and it's very hard to test everything in there. Do you still enjoy playing games, or you just look for fancy techniques in every game you run? So I actually still enjoy them, but I also look for fancy techniques in the one that I run. And for example, sometimes when playing, I will look at the character movement and see what kind of blends they have, if they have a feature of a character leaning to the side when they are running, because that's kind of what humans do, but not every game has it. So it's like a couple of things they try to imagine how they do in there. But it's still fun. Even if you even playing the same game that you spend like a couple of months or yes working on, it's still fun to play sometimes because as you work on it, you only see like parts of it. You don't see the whole thing unless you physically sit and play the whole thing. So playing after it's released, it still provides some fun because you see all the work that other people put into it, apart from the stuff you did personally. That's it, unless any new questions will appear. But it doesn't feel like it, so thank you. Thank you for coming to my presentation. I hope you enjoyed it, and thank you for your attention.